Hello, welcome everybody. We're really pleased to have Sir Dave King here at this Ask a Scientist session with Champions for Earth, and I'm going to pass over to him without delay. Thank you everybody for coming, and over to you, Sir David. Thank you for being here.
Thank you very much. I'm delighted to be addressing. I can honestly say I've never had so many sports personalities on my Zoom screen before, so delighted to meet you and to have questions from you after I've said a few words. What I'm going to start with is a very bare statement, and then I'll try and justify what I've just said. What we as humanity do to tackle the climate crisis over the next 5 to 10 years will probably determine the future of our civilization over the coming 2,000 years. So that's the bold statement. And now let me just start by talking about the extreme weather events that we've been experiencing over the past 3-4 years. And we have been experiencing these throughout the world. So the next slide shows just a picture of the sort of extreme weather events we've been experiencing. And these, in many places, have been incredibly extreme. Temperatures in excess of 5 degrees centigrade above the previous hot record in our time recording temperatures. And of course, massive floods. We are seeing a series of real changes in our weather system. And because we're all acclimatized to our own weather systems wherever we are, these events are causing havoc around us. And I'm going to just discuss the origin of these severe events. It's not often discussed. The Global Climate Crisis Advisory Group is a group of 15 leading scientists that I chair, and they come from 12 different countries. And we put out a report in August 2021 explaining the origin of these extreme weather events that were happening at that time. And so I'm just going to take you through what we were saying. In essence, in the Arctic Circle region, we have been experiencing extreme weather events, in particular high temperatures. So I'll take you back to the next slide, is just what has been happening over the past century, going back to 1850, to the temperature rise experienced as a result of global warming. You'll see that the temperature rise shown in black means that our global average temperature is now 1.3 degrees centigrade above the pre-industrial average. And in red, I'm showing you what has happened in the Arctic Circle region. And you'll see in the Arctic Circle region, starting about 30 years ago, the heating taking place there was roughly 4 times the rate of the heating for the average of the rest of the planet. And that's why I'm going to dwell on what's happening in the Arctic Circle region. I'll just take you, before I do that, to the next slide, which shows the European summer temperatures. Again, going back to 1840, when we began taking good measurements around the world, and in particular Europe. And you see in black the temperatures observed and taking the annual average. In red, the extremes of temperature observed during those years. And in yellow is the trend as computed by extremely good modelers working with whole Earth models of the temperature system. And these models predict into the future, but also they can be cast back in time. And this backcasting shows very good agreement between the theory in yellow and the experimental observations in black, going back in time. And the curves I'm showing you here were produced for me when I was Chief Scientific Advisor to our Prime Minister back in 2002. So you can see the predictions made from there on have been followed remarkably accurately. So these models are doing well. And going forward, you'll see to 2100, a temperature rise here predicted of 5 degrees, with extremes going up to an average of 6 and maybe down to an average of 2 degrees centigrade. And what this is saying is what the temperature rise will be if we don't manage to reduce emissions. And so far, we're still seeing emissions rising year on year. So this curve is what we would predict if we don't get better at reducing emissions. I've also shown here extreme temperatures, and you'll see that for example, and maybe you can't see it, 2003 was the hottest European summer temperature ever observed by humanity. And in 2003, we estimated about 60 to 80,000 people died of heat stress in Central Europe. The deaths have been reduced massively because people in 2003 were not anticipating anything like the temperature that happened. And you'll see now the temperature rises are way in excess of that temperature in Central Europe in 2003. Let me now move you on to explaining what is happening in the Arctic Circle region. So the next slide, a little bit of science coming in here, but it should be fairly clear, I hope. You'll see on the left-hand side, the Earth, with a cold Arctic, of course, so the North Pole always covered in ice for the last many hundreds of thousands of years. And that ice is covering both the Arctic Sea around the North Pole is all ocean, but also the land mass around the North Pole, which is also very cold and covered in what we call permafrost, because it's always frosted right through the year. And you'll see there that cold air, marked L, is contained in the Arctic Circle region by that white band. And the white band is what we call the jet stream. So this is a very strong wind that blows around the Arctic Circle region in an anti-clockwise direction. What that does is separate out the cold air up in the Arctic Circle region from the warm air coming from the equatorial region is marked H and colored red in this this picture. On the right-hand side is the current situation. And what we see is that jet stream has meandered very significantly away from being a circular motion. It's still a jet stream, but it's weakened as well as being meandering in this way. And the meandering means that what is happening, because the Arctic Circle is heating up, it is losing ice over the Arctic Sea. The blue sea soaks up sunshine, and so the North Pole region, now during the 3 polar summer months, becomes one of the warmer regions in the Northern Hemisphere. And so what we see is that the air above the Arctic blue sea, which is soaking up sunshine, the ice, of course, reflects sunshine back into space, soaking sunshine, warming the air above the sea as well. And what this means is that this warm air is pushing the cold air down. So we no longer protect ourselves from the cold air from the Arctic region. And in particular, you'll see over North America, the L marking the cold air coming all the way down. Texas experienced temperatures of minus 16 degrees centigrade. They never normally see anything close to 0 degrees centigrade, and there they were covered with snow. And this is now for 3 years in a row. This has happened in Texas. And then as that cold air comes down, the equatorial warm air, marked H, comes up towards the North Pole. This is simply keeping the mass of air constant. If some cold air is pushed down, we leave space for warm air to come up. We also see anomalies of high temperatures as well as anomalies of low temperatures. And the next slide, please. This is what actually happened in 2021. And you'll see it's marked June 29th, 2021. That jet stream got locked in along the west coast of America, North America, all the way up into Canada. Lytton in British Columbia, of course, is in Canada. And Lytton experienced a temperature like Canada has never experienced before. 49.8 degrees centigrade was recorded in Lytton. Now, this jet stream got locked in along the coast, as indicated here, for a good 3-week period. And what this meant was that people living in those regions along the west coast experienced extreme hot weather, 50, 55 degrees centigrade, as you approach the equatorial region. But in the Central America, cold and stormy. And on the east coast as well, very stormy, because this jet stream is no longer a very sharp jet stream. It becomes diffuse, and that causes all sorts of storms. And so what we know, for example, in Lytton, British Columbia, which is a very upper middle class town, very few people there have air conditioning. Who needs air conditioning in Canada? And 135 people died in that small town. And so there's the risk that we're talking about with climate change. None of us is going to be sheltered from the challenges that I'm talking about now. So all of this means that our global weather system has been seriously distorted. It is in transition away from the weather system that we were used to before. And if I could have the next slide. So what we see here is on the left, Greenland. Greenland ice is now melting irreversibly. Now, oh dear. So back to that slide. The Greenland ice, Greenland, how big is Greenland? It's about the size of Mexico. How much ice has been on it for hundreds of thousands of years? It has been building up for 1 million years, and the ice on Greenland is about 2 to 3 kilometers thick. And imagine the area of Mexico covered with ice to 2 to 3 kilometers. When all of that ice has melted, it enters the ocean, and global sea level average rise will be about 7 meters, 7.5 meters, 23, 24 feet. And so, of course, this will change the map of the world radically. Every city sitting on coastlines around the world will be well flooded by that time. Where I'm talking to you from, Cambridge in the UK, will be well underwater by the time we're at even a couple of meters above the present level. And so the map of the world dramatically changed by this. If we look at the center picture, this is the change in the jet stream driven by what's called the polar vortex, but let's leave that out for the moment. And you'll see that the North Pole towards the top of this sphere is not the warmest region, indicated by the reddish purple regions there. It's not the warmest region in the Northern Hemisphere at all. And in North America, you'll see the region is colder than the North Pole region. So this is the warm air pushing that cold air down. And on the right-hand side is another risk that until 10 years ago, the scientific community was not able to say very much, except that there is enough methane trapped in the permafrost that if it was all released into the atmosphere within, let's say, a 20-year period, global temperatures would rise by probably about 5 to 8 degrees centigrade on average. Right, so we're talking about the Arctic Circle impacting on the entire planet. There's not one region of the planet that won't be impacted by what is now happening in the Arctic Circle region. And let me just take you to the next slide, which is the slide that really wanted to come on, please. Next slide, which shows a hole formed in the permafrost in northern Siberia. People living in a village about 150 kilometers from where this hole appeared reported to the Russian government that an enormous explosion had occurred. They heard this enormous explosion 150 kilometers away. So what has happened here is a bubble of methane gas has been released from the ice and earth that forms the permafrost. It does grow grass on it, but it's mainly ice and methane. It's formed below the surface region, and when the pressure in the bubble is greater than the mass of the earth above it, the mass of the earth and the ice above it, it all blows off. And the methane is released into the atmosphere. How many of these explosions have occurred? It's in excess of 1,000 so far. So we're now worried that explosive release means that methane could appear in the atmosphere at a very significant level in a fairly short space of time. To date, the methane emissions from other sources, such as leakage from oil, gas, and coal recovery, and from agriculture, cows and sheep and so on, livestock in particular, a lot of methane is released from them, cow burps, and at the same time, rice production also produces a significant amount of methane. So the amount of methane so far emerging in this way has not caused major problems, but there's enough methane there that we need to be very worried about it. So we see temperature rises, global sea level rises, all of this threatening the way in which we live. Next slide, please. I am going to come up with a solution to all of this in a moment. So this is on two pictures of Vietnam. And Vietnam has a very large river flowing into it and forming a great big delta. The whole of the landmass of Vietnam is formed by this river bringing silt down, and the silt has built up so that Vietnam is above sea level, but it's not a long way above sea level. And we can now predict, as shown in the right-hand side, this is the new projection based on what I'm telling you, is that something like 90% of the landmass of Vietnam will be under seawater at least once a year. This is indicating what would happen at high tide. It's not indicating what would happen if there was a typhoon. A typhoon would add again to the water covering the landmass. Vietnam is the third biggest rice producer in the world. In the Delta region there, they've got enormous rice paddy fields. And of course, once the rice has been exposed to seawater, it will be salinated. Sorry, the land has been exposed to seawater, it will be salinated. It won't be able to be productive for rice unless we can produce a rice that is salt resistant. Across the water from Vietnam is another very big rice producer, Indonesia, which is an archipelago, and many of their paddy fields are also lying rather close to sea level. And in the southeastern coast of China as well, large paddy fields, which are very close to sea level. And the threat here is that in the near future, less than 30 years from now, we're going to see a massive challenge for food production for a population which by then will be approaching 8 billion people on the planet. So there's a very big challenge in terms of where people live, massive migration of people away. Bangladesh, we all know about. Cities like Calcutta, Mumbai, these cities are sitting close enough to sea level that the threat of them not being livable is on an even shorter timeline than this because of rising sea levels. So that's the nature of the challenge. And the fact is, it's in a very foreseeable future. It's not some distant thing I'm talking about here. All right, so what are we going to do about it? Next slide, please. If I could have the next slide. Yeah. I set up a Centre for Climate Repair at Cambridge. I worked for 4 British Prime Ministers, Blair and Brown, very successfully, and we set in place a climate change challenge for all parties of government. So we have a parliamentary climate change committee that commits itself and its government of any colour going forward in time to reducing emissions, and that's where the net zero emissions target comes from. But we're saying, yes, we must have deep and rapid emissions reduction. We've got to move away from fossil fuels as quickly as possible, and we have to stop removing forests as quickly as possible. And then secondly, we have to create new greenhouse gas sinks. Already there's an excess of greenhouse gases in the atmosphere. We're at something like 500 parts per million, and we need to bring it down to something like 350 parts per million to create a manageable future. It'll probably take us to the end of the century to get that, but this is a target that we really have to aim for to create a manageable future into the coming centuries. And then finally, to buy time, we have to stop what is currently happening in the Arctic Circle region. We've got to learn how to refreeze the North Pole regions, and in particular, keep the ice on land, Greenland, and the surrounding permafrost region. We need to keep the ice there and stop it from melting. And that obviously is a very big challenge. We're working on that challenge as well. And I can say a little bit about that if I've got time. I hope I have. So let me just take the next slide, please. So how are we going to remove greenhouse gases from the atmosphere at scale? Today, we are emitting in total carbon dioxide and methane around 40 billion tons of greenhouse gases expressed as carbon dioxide per annum. We believe that we have a system that should be capable of removing in excess of 3 billion tons of greenhouse gases a year from the atmosphere, and quite possibly in excess of 10 billion tons of greenhouse gases from the atmosphere. And this is a process that we've learnt about from looking at the behavior of whales, and this has only recently been established by the German scientist Smetacek. The baleen whales, these are whales with a very large amount of blubber, and they are very big whales. The blue whale shown here is the biggest of all of the baleen whales. The baleen whale, as shown here schematically, sails through the ocean about 300 to 500 meters below sea level with its mouth open, and just picks up krill. The krill is a very sociable animal. They tend to live in groups of billions, and once they find the krill, they just sail through and continue eating. And they can stay down there for a long time. They've got very large lungs, and their blubber protects them from the very cold water down there. And they have to come up for air, and we're very aware of that. And they come up and blow out, and we're very conscious of that from the spouting. And they suck in fresh air into their lungs very quickly. But at the same time, they have to do something else. The orifices of every mammal at anything like 300 meters below sea level are jammed shut by the high pressure of the water. And so the whales, when they come up, have got to do two things. One is breathe, and the other thing is defecate. They have to produce a vast amount of feces, and they do it very quickly. Whales tend to travel in pods, and if a pod of whales comes up, they may create enough feces in the sunlit area of the ocean surface waters. They may create enough feces to cover 1,000+ square kilometers with this nutrient material. This is like a farmer putting nutrient onto the farmland. And so within a space of 3-4 days, that area can turn green with phytoplankton. Phytoplankton, a green, fast-growing plant, is the necessary foodstuff for every fish larva. The fish larvae hatch from fish eggs, and whatever the nature of the fish, they need phytoplankton. Within an area like this, the phytoplankton means that the fish larvae survive and turn into little fish, whereas most of the oceans have no phytoplankton, and when the eggs hatch, the fish larvae die. Within a region of several hundred square kilometers, we may end up with something like 500 million fish within a month, within 6 weeks. And this vast amount of fish attracts sharks, of course, it attracts whales, it attracts all these bigger animals to feed on these vast amounts of fish. Now, I just want to stress, this project is called Marine Biomass Regeneration. What we aim to do is create, if you like, artificial whale poo. We're going to take the missing nutrients from the surface waters of the ocean that we're working in and spread them across the surface of the ocean. Hopefully we'll float them on the surface of the ocean, and we are testing how to do this now, by the way, using rice husks. So we're not using anything costing money. These rice husks are waste products of rice production. And these act as very tiny, effective rafts in the ocean. And we put this artificial whale poo on the surface of these rice husks, and that slowly leaches into the ocean surface. So I think you can see here the function of the baleen whales was to create these great green areas by fertilizing them with their own whale poo. But the blue whale, for example, is down to a population that is probably less than 1% of what it was 400 years ago, before we, humanity, started capturing them for their blubber. This was our first oil discovery, of course. And so we eliminated a very high proportion of these baleen whales very systematically throughout the oceans of the world. And there are some places where the whales remain, and particularly in the Southern Ocean, surrounding the Antarctic region. The Southern Ocean still has quite a bit of fertility, and there are a large number of krill living in that part of the ocean system. We believe that if we can continue this, and maybe it will take 40 to 50 years, we will recover not only the ocean fish and crustacean population, but also the whale population of the oceans. And in this way, we can leave the whales to continue to act in that fertilizer fashion. This is what we would call a circular economy. They eat the krill, and then they come up and bring the feces up into the surface, creating a continuous pattern of further krill and so on. That's the most effective way that we're working on, and we have a large global consortium so that we can work in all of the deep oceans of the world. At the moment, we're just doing experimental work, but within about 3 years, we hope that we can begin the process that I've just described at scale. Next slide, please. I need now to discuss how we are going to work on, if I've got the slide, yes, how we're going to work on refreezing the Arctic. Quite simply, if you are sitting in the direct sunlight, you're going to be getting very warm. And if you're on a Greek island, you're going to get lovely and suntanned. But if a white cloud goes over, then you're cooled down considerably. So what we're planning to do is see if we can create white cloud cover over the Arctic Circle region. That's a very large region for the 3 polar summer months of the year. Those 3 polar summer months is all we have to do to cool it. During the Arctic winter, of course, there's no sunshine around the 3 polar winter months, and a layer of ice grows over the whole of the Arctic Sea again. But this is just a thin layer, and when the sun comes back within a few days, that ice has gone. Roughly 50% of the Arctic Circle Sea is now exposed to sunlight during those 3 polar summer months. So can we maintain the presence of that layer of that thin layer of ice through the Arctic summer by covering it with white clouds, and then continue that year on year and regrow a thicker layer of ice over the Arctic Sea? We indicate here the sort of time scale that we're on. We've done the first experiments last year, and we are now genning up to do a significant amount of experiments from Goa in India, from Hawaii in the United States and in the Pacific, of course, Goa in the Indian Ocean, Cape Town in the southern Indian Ocean and in the Southern Ocean. And we are also talking to a group that would take us well into the Atlantic. So these large-scale collaborations are critically important to manage the type of process that we're talking about in the removal of greenhouse gases from the atmosphere. But in terms of marine cloud brightening, we're also working in Australia. Why Australia? Because of the the Great Barrier Reef off the east coast of Australia. So what we are doing is working with a very strong Australian team at Southern Cross University in Australia to see if we can cover the Great Barrier Reef with white cloud cover for a significant part of the year to cool the ocean water over the Great Barrier Reef and hopefully sustain that reef, which, as you all know, I'm sure, is rapidly dying at the moment. So that's just a very quick picture of the nature of the risk we're faced with, the solutions that we're coming up with. What do we need? We need finance. That's really what we need. Every penny that we are spending at the moment is raised from philanthropists and from philanthropic bodies set up by philanthropists. So it's a big target. When we look at the marine cloud brightening, what is the cost of running these vessels? We'll probably need 500 to 1,000 of these vessels surrounding the Arctic Circle region. Running them will cost £2 to £3 billion a year. Building the vessels, perhaps up to 50 billion. But the extreme weather events I started off talking about are already costing us, on the, all of us together, a good $250 to $500 billion a year. So we're looking to try and stop the loss and damage that is occurring around the world. So the next slide just takes you to the very end point of my talk, and I leave you to Q&A.
Well, thank you, Sir David King. That was really incredible. Every day is a school day, and I'm really, really happy to have heard from you there.